Last week we made observations about the moon, and you even sketched them and maybe used binoculars to see the moon. But how do we see the moon? Why do we see the moon? And or anything else for that matter? And it's because of electromagnetic waves. Electromagnetic waves are a traveling disturbance. There's a disturbance in one place, and that disturbance travels. It's different than mechanical waves like water waves or sound waves or seismic waves, where there's actually molecules they're going through. Electromagnetic radiation can go through empty space. It can go through a vacuum. And it's partly because of what it is. It is an electrical field and a magnetic field. We know from class that electricity can make magnets and magnets can make electricity. Well, a changing electrical field creates a changing magnetic field. And the two kind of just keep making each other over and over and over and travel through space. Now certainly it dissipates and it gets weaker because it gets spread out more, but it travels literally forever. And at a constant speed, the speed of light. All electromagnetic radiation, for the most part, travels at the speed of light, 186,000 miles per second. If you think about that, the moon is 240,000 miles away. So it takes the light that you see right now has been traveling to your eyes from the moon for about a little over a second, 1.3 seconds. I should point out, though, that the light that you're seeing from the moon is reflected sunlight. The moon doesn't create any light of its own. It's just reflecting the electromagnetic radiation that comes from the sun. And speaking of the sun is 93 million miles away, so it takes that light traveling at the speed of light to about 8 minutes and 20 seconds to reach the Earth. While I have the model in my hand, last week when you observed the moon, it was over on this side of the Earth, and it was visible all night long. Now it is over here, and you won't see it until after midnight when the Earth is rotated and you see it in the morning skies now. And in another week or so, it won't be in the nighttime sky at all, and then in another week it'll be visible in the evening again. And that moon cycle takes a month. The basis for a month is a moon. So electromagnetic radiation is bouncing off the moon, and that's why we see it. That electromagnetic radiation, that wave, enters our eye. It passes through the cornea and then through the iris, and the hole in the iris is called the pupil. And then it goes through this lens, and the lens is curved just like a telescope lens, and it focuses that light from a single point out in space or on your wall or whatever, and it focuses that to a single point on the retina. And on the retina are different cells that can see different colors. And when a red wavelength of light hits a red cone cell, it sends a signal to the brain, and that fills in that pixel, I guess, in your brain. And your brain puts those millions of signals. There's a whole bundle of nerve fibers called the optic nerve that go to your brain, and your brain interprets that and gives you the image, the impression of what you see is what you see. But it's kind of wild that it's just electromagnetic waves being changed in the back of your eye to an electrical impulse, a little signal going down a wire to your brain, and then your brain puts it all together. Now, your eye is tuned to detect, we call it visible light, red, orange, yellow, green, blue, violet, the visible spectrum of colors. But there's a lot of other wavelengths out there. There's radio waves and microwaves and infrared, what we commonly call heat waves, and then visible light. And then there's gamma rays and X-rays and ultraviolet rays, waves. All of those together are called the electromagnetic spectrum. What your eyes can detect is just a little tiny part of that. But we can have telescopes that detect X-rays and can give us a picture of the universe in X-rays, and that will give us a little bit different information. We can have telescopes that detect radio waves and give us a picture of the universe in radio waves, and that tells us a little bit of different information. And we can put all of that different information together to come up with our understanding of the cosmos. And because we can't go there, you know, humans in the history of humans have only been this far. And only a few, 12 people have walked on the surface of the earth, or on the surface of the moon. Those are the only human beings that have ever left the Earth's gravitational pull. And the moon is still in the Earth's gravitational pull, but you get it. 12 people, 5 countries have landed on the moon. Only the United States has landed people on the moon, or anywhere else for that matter. Here's a short video on electromagnetic waves put out by NASA that explains it in a lot better fashion than I could.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. 1 wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
I don't know where I was going with that, so we'll end that.